In this first practice problem, we're asked to determine the empirical formula of a petroleum compound. Petroleum brings to mind fuel. You're absolutely right. It is a hydrocarbon, and it's going to burn very well, making it suitable for combustion analysis. The tricky part about this particular problem is that we don't know if the compound contains oxygen. So we're going to start the process the same. We're going to take our mass of carbon dioxide and convert that to moles of carbon dioxide and ultimately moles of carbon. After that, we take the mass of water, convert it to moles of water, and then using the 2-to-1 ratio, the formula can remind you of that, determine the moles of hydrogen. Now that I've determined the moles of carbon and the moles of hydrogen, I can use those values along with their atomic masses to calculate the mass of carbon and the mass of hydrogen in my petroleum compound. The big question then is there any oxygen in that petroleum compound? So I'm going to use the same approach that I used in previous problems to determine how much oxygen is in that compound. I'm going to take the mass of the compound before they burnt it, so 12.501 grams. And I'm going to subtract out the mass of carbon. As well as the mass of hydrogen. When I did that, I got an odd result. I got negative 0.02445 grams. So that bothered me a little bit. How can I have a negative mass? Well, one thing's for sure, we probably don't have any oxygen in that original compound, not with a negative value here. What happens? There's a bunch of things that could have happened. One, they like to give us data that's based on actual laboratory data, and there's always small sources of error that occur when we're doing some kind of combustion analysis. So the numbers may be slightly off, not too bad, right? We're still getting a 0 at the end of the day, but they might be slightly off because of small errors in the lab. Secondly, our periodic table, right? I'm using the values that are rounded to the hundredths place. So maybe that's having a tiny impact. Third thing, I've been kind of lax about my rounding. I haven't really kept the whole value the whole time because it's the empirical formula that I want, and I don't have to super worry about sig figs. So all of those things may have contributed to the fact that I don't have exactly 0 after my subtraction step. But since I have 0.02, I'm going to go with the fact that there's no oxygen in that petroleum compound. All right, so after that, I still need to determine the empirical formula of the compound. I'm going to grab the moles of carbon and the moles of hydrogen. Looks like carbon is the smaller of the two, so I'm going to divide both values by the moles of carbon. That gives me, well, carbon will be 1 because we're dividing it by itself. Hydrogen, again, talk about weird results again. Hydrogen is 2.398. So I'm like, well, what do I do with that? That's not close enough to 2. It's not even 0.33333 where I can multiply by 3. So I decided to rewrite this as 2.4. And then I started thinking, what is 2.4? Like, it's a decimal, but what does it look like in fraction form? So here's my thought bubble. And I'm thinking 2.4 is like 2 and 4/10. But, 4/10, why would I write it like that? 2 and 2/5. And And then that gave me the idea to take advantage of the 5 on the bottom of the fraction, because we want to eliminate the decimal or the fractional part of this to obtain a whole number ratio. So to get rid of the 5 on the bottom of a fraction, you multiply by 5, right? So that's what I'm going to do. I'm going to take this result, the C1H2.4, and multiply the whole thing by 5. And when I did that, I got C5H12. And that's the empirical formula of the petroleum compound. Typically, I like to select problems that are realistic. I have a couple qualms with this one. This problem is about a class of compounds, actually, known as PCBs. That stands for polychlorinated biphenyls. And they were originally manufactured and produced to cool electronic components. And it seemed like the miracle compound because they don't degrade, so they don't break down when they're taking in all that heat as part of the cooling process. Sometimes, as you familiarize yourself with the more negative side of chemistry, sometimes the properties that make compounds, chemical compounds, so attractive are the same properties that cause problems long term. So these PCBs weren't degrading in the microwaves and other electronic things that they put them in to serve as coolants. Yet on the flip side, when the PCBs were disposed of, they didn't degrade in the environment either. Rather, they remained in the soil, in the water, and they're also subject to biomagnification. So if an animal takes it in and you eat that animal, then you're going to be taking in the PCB as well. And they are carcinogenic, and they're still around, even though they're banned in the late 70s, because like their original property, they just don't degrade that readily. And so I like that aspect of it. Maybe it gets you thinking about some of the more negative consequences of chemical manufacturing. And I'm all for chemistry, right? But there's pros and cons with everything. But on the flip side, we can't burn these. So they don't degrade. You'd have to use such high temperature. And then at that point, the combustion reaction, because it contains chlorine and because you're at such high temperature, becomes a lot more complicated. So it's not going to follow that same pattern that we've been used to. So that's like the unrealistic part of this problem. However, I do like this problem in that it forces us to consider how can we use combustion analysis to analyze something that may contain other elements apart from carbon, hydrogen, and oxygen. The first steps here are going to be the same. We're going to take the mass of carbon dioxide and convert it to moles of carbon dioxide. We're going to take the mass of water, go to moles of water. Don't forget to multiply by 2. At that point, since we know that the PCB only contains carbon, hydrogen, and chlorine, we're going to use the same kind of technique that we did with the oxygen. We're going to get the mass of carbon and the mass of hydrogen, subtract these values from the total sample of the mass, there it is, and then the leftover we're going to attribute to the chlorine in the compound. Let's do that. I took the mass of the sample before combustion, subtracted out the carbon and the hydrogen, and I'm going to attribute the remaining mass to chlorine. Can't really do much with the mass of the chlorine, so we need to convert that to moles of chlorine. And this should look similar to what we do with the oxygen, except instead of dividing by the atomic mass of oxygen, I'm going to use the mass of chlorine. So at that point, I obtained 0.015325 moles of chlorine. the 2 mole values that we previously determined. So now I'm going to update this to include the chlorine mole value as well. Looks like hydrogen and chlorine are in a tie as being the smallest of all the mole values. So 0.0153, they start deviating a little bit at some point, but I don't think that's going to matter. So I'm going to divide everybody by 0.0153. And that gives me a value of 2.4 for carbon. Hydrogen, since I divided it by itself, it's going to be 1. And the same thing with chlorine, that's also going to be a 1. Now we're in that situation again where we have a number that we have to multiply to get a whole number. So I'm thinking, thought bubble here, I'm thinking 4/10. 2.4 is like 2 and 4/10, 2 and 2/5. So this whole thing needs to be multiplied by 5. And when I do that, I get C12 H5 Cl5. Now that we've established that the empirical formula of the PCB is C12H5Cl5, our next job is to determine the molecular formula. We're given a molecular mass, and we need to calculate the empirical mass. So I took all the values and did that. Lo and behold, our empirical mass is the same as our molecular mass. And this does happen. And that means that they're a 1-to-1 ratio. They're one and the same. So our molecular formula then is also going to be C12H5Cl5. Here we're asked to analyze caproic acid. It's a stinky compound associated with goats and gym socks and all kinds of stinky things. It's a hydrocarbon, so I'm going to take the mass of the carbon dioxide that was produced when it was burnt, turn that into moles of carbon. It's a 1-to-1 ratio. Mass of water, turn that into moles of hydrogen. Remember, that's a 1-to-2 ratio, and you need to multiply that by 2. The problem is kind of ambiguous. We're not told one way or the other if the caproic acid contains oxygen. So we're going to have to go through the process to see if there's any leftover mass that we can attribute to the oxygen. That's why I took the moles of carbon, converted it to grams of carbon, moles of hydrogen, converted that to grams of hydrogen. After that, I took the mass of the caproic acid before the combustion analysis and subtracted the mass of the carbon and the mass of the hydrogen. That did give me a significant leftover value, so I'm going to say that it does have some oxygen. The mass of oxygen is then used to determine the moles of oxygen. Setting it up here, these are all my mole values. Oxygen has the smallest mole value. So I'm going to divide all of these numbers by 0.007746. That, for the first time today, gives us some nice even values. We get carbon with a 3, hydrogen with a 6, and oxygen with a 1. This is our empirical formula. And our last step is going to be to use the molecular mass to determine the molecular formula. The problem told us that the caproic acid had a molecular weight of 116.2 grams per mole. We just determined the empirical formula, so I used this formula here, C3H6O, to calculate the empirical mass. That came in at 58.09 grams. Whenever you're trying to establish the molecular formula, you're going to take your molecular mass and divide by your empirical mass. That gave us a ratio of 2:1. So that means that the molecular formula is twice as big as our empirical formula. So I took the C3H6O multiplied by 2, and that gave us a molecular formula of C6H12O2.